Yeah, so as Valerio said, my name is Nicolas Duboc. I'm a PhD student here at UBC under the supervision of Dr. Roland Stull, and I'm part of the weather forecast research team. And today I'm going to be talking to you. It really is a poster that I presented at AMS with some preliminary results of my research. Um, I then sort of transformed this into a presentation, which typically only went for 15 minutes, but I will try to talk slowly and try to get into detail. And hopefully you can have some interesting discussion and questions after. So without further ado, using spectral filtering techniques to modify WRF. Um, so just a little bit of background, right? Complex forecasting complex terrain is typically tricky for numerical weather prediction. And it's really due to the reason of the way that these equations of motion are discretized, specifically in what kind of wave number or wavelength can be advected across the terrain before we have some issues. And this limits us sort of in the time step, in our grid resolution, and in the maximum wind speed in the model. So to try to sort of mitigate this, models like WRF, after interpolated to some user-defined grid, then employs this terrain smoothing. This eliminates these wavelengths that can be somewhat problematic. But the problem with this is that it significantly reduces the amplitude of the terrain. So it raises up valleys, cuts off mountaintops. And they quickly realized that just doing a smoothing just isn't realistic and doesn't give a good verification results in the mountains. So they developed this smoothing, de-smoothing technique which smooth the mountains out to sort of maintain stability of the model, but then sort of try to regain some of that amplification in the mountains in order to have some more realistic terrain. But unfortunately, a lot of different studies have shown that this was just simply not enough. So the picture on the lower left there is a von Neumann stability analysis on the Runge-Kutta third order in space fifth order in time scheme, which comes default in WRF for horizontal advection. You'll notice that at a non-dimensional wave number of about 3.5 or 3.6, we have a pretty high instability at really high Courant values. So, with this in mind, I'll turn your attention to the plot on the right. This is basically a response function of the default terrain or the default smoothing method that WRF uses. All you need to know about this plot currently is that it's basically just showing you what wavelengths are passed or what wavelengths are kept in the model and which wavelengths are attenuated. And you'll see the closer that we get to this sort of critical wave number here, the less amount of these wavelengths that we have in the actual model. Um, and this is what it looks like in practice. I do apologize as well. This is an old plot, and it's the only plot that is not consistent with the colors of the plots that you'll see in the rest of this presentation. Um, but the gray line is what I'll classify as our truth data set, which is essentially just a 7.5 arc second terrain data set from USGS. And it is what is used as original input into WRF. So this is what WRF sort of interpolates. The red curve is that interpolation or this block average interpolation that WRF does. And then the dashed blue line is the terrain after it has gone through the smoothing and de-smoothing algorithms in WRF. So the blue curve is really what the model determines is the actual terrain. And it's what the modeled weather interacts with inside the model. So, filtering as a possible solution. So, spectral analysis is really useful, right? Because it kind of treats our terrain like any other signal or an image, and we can decompose it using Fourier transforms or wavelets. Um, so, using this von Neumann stability analysis, I originally just didn't know where to start, right? So, what is which wavelengths are just too much for WRF to handle? So, I used this horizontal linear advection, which is a super big simplification on the actual advection that goes on in the model to sort of gauge like a point where I can pivot, right? So a point where I can test wavelengths that are smaller than this point, greater than this point, and then sort of gauge how the performance of the model, how the model behaves when I'm modifying terrains at the range of these wavelengths. So I used it to sort of gauge where I can start and then got this block average terrain or this interpolated terrain by WRF. I transformed it into spectral space using the fast Fourier transform. Again, you could do this again through wavelet decomposition. I'm focusing for the sake of this talk, for the sake of the talk that I did at AMS, just focus on fast Fourier transforms. The spectral terrain, then I multiply it by a response function. And a response function just basically prescribes the range of wavelengths that are either passed, attenuated, or in this case, amplified. Um, and then sort of transform the terrain back into physical space. And then this is the terrain that's used as input in WRF. And I have this little schematic down here from the WRF user guide that kind of just shows you the overview of what WRF, of how WRF works. So it starts with these external data sources, it goes through this pre-processing system, and then finally goes into the actual WRF model. We're focused on this area here. So we're looking at the static geographical data, which again tells us what our land use is, our terrain is, etc. The circle really should be over all of GeoGrid, but in this area is where we have this terrain interpolation and this smoothing. So what I do is I allow the model to interpolate to the user-defined grid. But after it's interpolated, but before it's smooth, I basically yank it out, do my own smoothing and amplification, and then I throw it back in there. And then it goes and interacts with MetGrid into Real, and then eventually into WRF. So just a quick recap of Fourier transforms, right? You've got a signal in time or in space, and what the Fourier transform essentially does is just decomposes this signal into its fundamental wavelengths. And you can see that here. So this is what our Fourier transform looks like. Once we do it, we see that we have our frequencies at different amplitudes. And again, just like a visual way of this whole process, we have, this block average terrain or this interpolated domain, in this case, the 27-kilometer domain. We perform a two-dimensional Fourier transform, and we're stuck with this raw power spectrum. Now, unfortunately, we're sort of limited by the Fourier transform because it requires our signal to be periodic. But as you can see by this image, it is not periodic. And the issue with this is that these discontinuities at the borders or at these edges are going to show up as these like spurious high frequency noise in the data set. So in order to sort of mitigate some of this, I multiply it by a low pass filter by using a Hanning window, which is a window that a lot of different other studies have done, specifically looking at terrain and evaluating it from a spectral perspective. I then have this windowed spectrum and multiply it by these response functions, which again is just prescribing which wavelengths are passed, attenuated, or amplified in the model. I then do a two-dimensional inverse Fourier transform, and I have my filtered and amplified terrain in physical space, and then this is used as input into WRF. So from this, I asked two main questions. The first one being, so what difference do these varying response functions have on the terrain representation in the model? So how different does the model look like? Does it look more realistic, less realistic, depending on the range of wavelengths that I decide to amplify? And then can reamplification of certain key wavelengths, whichever these wavelengths are, produce more realistic terrain atmosphere interactions? Because that's really our goal here, is to have more representative terrain in the model in order to have better verification results. So I'm talking about this response function, and I've told you that it's just prescribing it. But how do you actually calculate it in terms of when you have terrains that are different? The response function is essentially just a ratio of the Fourier transformed of the smooth or amplified terrain divided by its block average terrain. So that'll tell you exactly how much of a certain wavelength is present in a certain data set. So this black curve here, for example, is the default WRF smooth desmooth algorithm, and I've labeled it as WPS. And the reason I've done this is because if I add the smooth desmooth, this box gets huge, and it messed up my plot for my poster. So I just call it WPS, but that's what WPS stands for. Each colored curve is representative of a different range of amplification. There are two different sets, right? So the green and the blue, so AMP1 and AMP3, amplify wavelengths that are below this critical wavelengths, and amplification 2 and 4, the orange and the red, do the same thing, but for wavelengths that are significantly greater. And the difference between these two in each set is how far in range they amplify certain wavelengths. How I had determined how much to amplify, yeah, this part was a little was a little janky, but what I essentially did is I did a rough cutout of the 7.5 arc second digital elevation model data set, and then I took a percentage difference between the interpolated data set and the 7.5 arc second data set, and just multiplied. That's the multiply the amplification factor that I used. which changes with each domain that I decide to test. Um, but speaking of testing, right? So how do I test this? Three main domain configuration that I'm looking at currently. The first one is a single 27 km resolution grid. Um, I put here larger grid spacings equals greater smoothing. But what does that mean exactly? Well, if you think about it, it's actually super intuitive. If you have one point every 27 kilometers, you're averaging quite a bit of terrain. So you are smoothing or you're eliminating a lot of really important terrain features, which might be important. And the way that WRF does it is it just averages pretty equally on the entire grid cell. So this is a grid spacing that benefits pretty greatly from this reamplification because we can sort of get these peaks back so that we might have lost from averaging such a large area. Um, I'm also working on a single grid, 9 km resolution. This is sort of a gray zone for convective parameterization. I believe it's um, 6 to 12 km. I might be wrong, minus plus or minus 2 km resolutions. But this is called a gray zone for corrected convective parameterization. So in 27 kilometers, for example, we're definitely parameterizing things like cumulus, microphysics, and a bunch of other stuff. Um, when you get down to these, 12, 8, 9, 10, we're sort of in a gray zone where certain parameterizations are useful for cumulus and microphysics schemes, but sometimes they're not all that useful. There's also a lot of scale-aware schemes that are specifically designed for these grid resolutions. Um, and there's been a lot of different studies to see how these schemes sort of behave in areas of complex terrain. And I guess the question I'm asking now is, well, now that I've remodified the terrain and I'm getting technically more realistic terrain, how do these parameterizations or the rankings of these parameterizations um, affect the results? And finally, I'm working on a nested grid, a 9, 3, and 1 km grid. And this is really just to evaluate smaller values. And you can see that here on this plot on the right-hand side. So these plots down here just show you examples of 27, 9, and then the nested domain. The plot all the way on the right, this is, for example, focusing on the Kelowna Valley. So in 2023, some of you may or may not be aware, there's a really big fire in Kelowna that started on the west side of the lake. Around 9 p.m., they experienced really strong downsloping winds from the west, which then caused the fire to jump from one side of the lake to the other. So this is one case study that I am taking a look at currently. Um, so for the sake of this talk, although now that I'm thinking about it, this talk maybe would have benefited from going through all of these case studies, but unfortunately, I'm still working on two of them. But for the sake of AMS, I only really focused on one of these grid configurations, that is the 27 km grid spacing. And to Oh, right. So just a quick comparison, right? So we've been talking a lot about what the spectral response does to the terrain and how that response, what that response looks like when you've actually applied it to the terrain. So again, the top left plot here is our spectral response that I've talked to you before. The right, I'll ask you to ignore the color bar and ignore the title and really just focus on this dashed line with these stations that you see here, because that is the plot that I'm showing you, or the slice that I'm showing you down here. Um, Now, again, you've seen this plot a little bit before. I apologize for the inconsistencies in the coloring. Um, but again, the gray is what I'm determining is our truth data set, which are 7.5 arcsecond from USGS. The black dashed line is the WPS smooth, desmooth default algorithm. And then each colored curve here corresponds to the colored responses that you see up here. And you can see immediately from the results, for example, if you're looking at the blue and the green, these are amplifying wavelengths that are significantly smaller. And you can see that in the model. It resolves relatively the smaller wavelengths a little better than, for example, the red and the orange, which we can see since I'm amplifying wavelengths or letting wavelengths pass through that are significantly larger, it does do this over smoothing. And you can even see the ranges, right? Because the difference between the two sets that are start before this critical wave number or critical wavelength and past this critical wavelength is really the range in which they go, right? So for example, this green curve goes out significantly more than this blue curve. And for the most part, you can't really notice a lot of that difference until you start getting to the end. Once we start getting into the prairies, you can see that this really longer wavelength is amplified and really reduces our elevation by quite a bit. Whereas, the um the blue curve, which is a significantly smaller range of wavelengths, actually captures this pretty well instead. Right, so a case study. Like I said, I kept it super simple for AMS. And I just looked at a pretty famous windstorm that happened here in British Columbia in 2018. So again, I'm looking at a single grid, 27-kilometer grid spacing. The top left plot just gives you sort of a synoptic overview. I'm just showing you 10-meter wind field and sea level pressure contours. The plot to its immediate right shows you the radially average power spectral density ratio, which is definitely a mouthful. But it's for the same time step. But what this is, it's just essentially it's that 2D spectrum that I showed you before. It's averaged over a radius of one wave number, and then I'm dividing it by this smooth case. And that's why you can see, for example, this black line here at 1 is this WPS over this WPS, and each color curve is just the case over the WPS. So one thing you'll notice, uh, if you remember what the response functions look like, is that we have peaks in power, or this ratio that is very closely related to the peaks that we see for a spectral response. So what this is essentially telling me is that the scales that are being amplified in the terrain is directly affecting the scales of the wind field, which I thought was a really interesting thing to find. So now I'll direct your attention to the bottom two plots. So on the left plot, I'm basically just showing the mean absolute error and the differences between the amplified cases and the smooth cases. So the blue dots indicate that the amplified cases are performing a lot better than the smooth cases. Um, so the first thing you'll notice is actually how crazy inconsistent it is. We have some blue dots that are right next to some really red dots. Um, and you can also see that really clearly by the plot to its immediate right. We can see the performance of each of these, each case on these select stations. Um, and this was sort of tricky. I got these results actually the week before AMS. So that was nerve-wracking, but I did want to have something to explore. But when it comes to the question of why is this the case, the first thing that came to my mind was, well, what is the elevations of these stations? And where does the model think that these stations are in terms of elevation? And for most cases, yeah, the model was definitely not getting for particularly Squamish, it was not getting the exact elevation right. But something interesting is that the difference in elevations between each model is actually not that different. So what is going on? My current theory actually has something to do with these two plots that I'm showing up here, where changing different scales in terrain or amplifying different scales in terrain then has an effect on the wind speed scale as well. And what I think is going on is that different stations are simply being affected by different scales of the wind speeds. So for example, Comox Airport is maybe affected more by the smaller scale winds. Whereas Squamish Airport might be a little bit more affected by the larger scale winds. And that this might be why we're seeing pretty much the complete opposite performance of each of these in each of these two stations. Um, so again, some initial findings. Stability is still possible, even below a critical wavelength. But we kind of knew this already, right? Because I did the von Neumann analysis for horizontal linear advection, but we know that the advection in WRF is not necessarily linear, and it's definitely not in one dimensions. And it's most common, the most common stability issues that we have with WRF is honestly in the vertical anyway. But again, this just was used to give me a starting point. Um, on the right here, so terrain amplification impacts 10-meter wind fields for all cases, and it scales similar to the terrain amplifications. And this goes to what I was talking about earlier. Like I said, I don't have to really change that because they're both here. But changing different scales in terrain gave me different types of behaviors in those same scales in the wind field. So it'd be interesting to see how other meteorological variables behave in this case. And how if maybe you'd want to capture different scales if only modifying those scales gives you better performance or better verification metrics. And again, the range of amplification is very crucial, but it is really inconsistent across these observations. And again, when I was in AMS, my first thought was, well, elevation. Elevation is not the case, so what else could it be? Thinking more about it, it might be. My running theory is again that the different modifications of different scales affects the wind fields, and then each station is affected by a different scale of this wind field. Um, oh, Right, so some ongoing work, and believe me, I have a lot of work to do. First, I'd like to uncover the limits of model stability. So I've already proven that even though that the model can still run, even though we have higher wavelength features in the terrain. So just off of what WRF has as a default, can modify the terrain and allow greater amount of those wavelengths to be included in the model without having it break. But I really want to break it, mainly because I want to find a lower bound. I use the von Neumann stability analysis to sort of, well, maybe we can try around this area, but I really want to find like a definite bound. Um, I also want to test just larger ranges of responses and different combinations of these amplifying values. And this kind of goes back to what I was saying about modifying the different scales of the terrain and what kind of impact that has. In this case, in the 10-meter wind field, but I'd also like to take a look at other variables, G potential, temperature, relative humidity, etc. Um, and there's a lot of different domain configurations that I want to take a look at. WRF has a variety, well, not a variety, but a few different parameterizations for gravity wave drag and gravity wave damping. Gravity waves have a tendency to either leak into the stratosphere or be absorbed by the planetary boundary layer. And this sort of modulates how much or how they decay in space and in time. And with this, again, reamplified terrain, first I'd like to take a look at just gravity waves and how they behave in the province of British Columbia. Um, I don't know if you guys saw the map of British Columbia. Uh, if I just cut it out here, it is like 80% mountains. And aside from being 80% mountains, it has a lot of really it has a lot of complexity to its terrain. And I'd like to investigate a little bit of how these gravity waves behave in British Columbia and how this sort of changes when I reamplify the terrain. Um, and speaking on gravity waves and just upper level winds in general, these higher peaks in theory lead to a less reliance on gravity wave drag parameterization. So how does this higher topography impact the need for this parameterization? I know, for example, one of the parameterizations for gravity wave drag in WRF essentially elevates the terrain in order to produce some of this drag, or pseudo elevates it in order to produce some of this drag. So now that I'm re-amplifying peaks, is that necessary? Or how does the parameterization, or is that even better? How does this parameterization behave once I've elevated these peaks? I also want to try different physics schemes. Like I mentioned before, there's been a previous study, particularly by Dr. Jaworek. She did a lot of investigating of cumulus parameterization, microphysics parameterizations, land use parameterizations using the default terrain in British Columbia. And she found some pretty interesting results. But how does this change with this new terrain? And the focus of this isn't super fleshed out yet. She looked at just basic um, uh, uh, sort of precipitation regimes, depending on whether it was winter or summer. I might want to take a look a little bit on snowpack, particularly in the Alpine, since I am working with really high terrain and sort of how this might affect stream flow. I'm still not sure yet. This is part of my proposal that's currently being written. So it's a lot of stuff still up in the air. Um, and then, yeah, like I mentioned, I tried different amount of domain configurations, right? So nested versus non-nested domain with and without domain feedback. If I modify the terrain in the parent grid domain, how does that affect a child domain or a nested domain um, that doesn't have this sort of amplification, or maybe how does the amplification in a smaller domain affect the parent domain who might not have, or maybe if they both have it, what kind of performance do you get in that? Um, yeah, and with that, I do apologize. It seems it's only 30 minutes. Thank you very much for the opportunity to be able to talk. I really appreciate it. here's the poster, just to prove to you that there actually was a poster. I do apologize. It looks a little janky. It looks like when I moved it from one PowerPoint presentation to the other, some things just did not want to go go transfer all that well. But here are some references. But I'll just leave you with this since all of the information is here anyway. Thank you
Uh,
very much.
well, thank you very much for the great presentation. And I guess we can open up this to questions. If people have questions, let me see. Yeah, we have virtual applauses. Yeah, that's the downside of presenting on Zoom. You only get hands and symbols. Um, well, I had one question, um, and, and maybe it's kind of obviously going too far, but in several parts, you were mentioning things that sounded like interesting hypotheses. You were mentioning, for example, different stations affected by different type of winds and so on. Although this might be way beyond the scope of the specific work, do you have a sense of what could be done to validate some of those questions, those hypotheses?
Yeah, really good question. Validating and verification, I think, is one of the most difficult aspects of this project. Um, Mainly because, how do you validate with such sparse observations in such complex terrain? Um, this is still a working theory, but for me, the way I see this is focusing on particular cases where I'm expecting certain scales of either wind fields or whatever meteorological variable I'm looking at. I'm expecting those to be the governing factors of why we have a certain result at a particular station. So using those as a benchmark, I would then modify terrain at those scales and see how it performed similarly to each individual case, which sounds tedious because yeah, it is pretty tedious to do.
Okay, thank you. I see Mustafa has a question.
Yes, thanks, Valerie, and thanks, Nicholas, for the talk. So, as a person who is not completely familiar with your field of studies, I have a couple of maybe basic questions. So, these essentially by scale, which is kind of a naive question because you keep repeating it through your presentation, but I'm not quite sure. Are you referring to temporal scale or spatial scale for your model?
So it's the spatial scales. So I'm modifying the terrain. So yeah, I should have been more clear in that. But when I talk scale, I do mean yeah, space, not necessarily in time.
Okay. And then when it comes to the stability of the model, you're referring to the numerical stability of your PDEs, underlying PDEs, or what do you mean exactly by the
Yes,
stability?
sorry, I did not mean to stop sharing there. I was gonna go back to a slide. Yes, when I mean the limitations of the model, any numerical model, is limited by this Courant number, right? Which basically uses the combinations of, this, for example, is how they've described it in the WRF user guide. But you can move these variables around and mess with this inequality in order to have this CR theory in and of it by itself. So for this case, for example, we have our time step needs to be less than um, this combination of our theory of what our Courant value is, which is again produced by all of these metrics, at our grid resolution and what our maximum wind speeds are. This root 3 here is put in because it is a three-dimensional advection. So for example, in this case, the Runge cut a third order in space, fifth order in time, I believe is that the yeah, so the Aeronaut 3.5 here, for example, has a limiting Courant number of about, 1.43. And this is what our CR theory is, or this is what the model determines that this CR theory is. It then divides it by this root 3, multiplies it by this, and then it ensures that this time step is reduced. And Mo WRF and a lot of different models have this adaptive time step, right? So this delta T max will be modified as the model continues to go in and evaluates the wind speeds, given this theoretical Courant number and this
Excellent.
and this.
Do
grid
we have time,
resolution.
Valerio, or can I ask a follow-up or?
Yeah,
Yeah,
absolutely.
Okay, excellent. So and again, this is completely from a person who doesn't know this field. So this equation you're showing is because we do have a scale invariant methods when it comes to solve like spatial PDs related to spatial models, right? So where is this limitation in your model coming from? I mean, this looks like tying the temporal scale, if I understand it correctly. Delta X is your spatial scale, delta T is your temporal scale. Okay,
Yep.
so this ties an it kind of defines an upper bound for your temporal scale, which is a little bit surprising to me because we do have a scale invariant models for solving PDs, which I assume is the underlying equation going in your model. So what is the physical phenomena that ties your temporal scale to spatial scale of the model is my question.
Yeah, and see if I understood this question correctly, but this is again specifically what WRF uses and what they've determined to be their limitations. What we're worried about here is if we're advecting a plume, let's say for example, a Gaussian distribution of water vapor, as we advect it across the domain, given a given grid resolution and a given time step and a given wind speeds. Unfortunately, there are values of wind speeds that, yes, we do have an upper bound for our temporal scale, but there are certain values of wind speeds which might cause this Gaussian plume to either be reduced, like significantly damped, or blow up to some unreasonable value. And then this is why while you do have, again, an upper bound for this temporal
So
scale,
it's a
you,
fluid dynamics type scenario that is coming from, right?
yeah, essentially, yeah, it is from
Excellent.
a, yeah,
Thank you. Yeah.
you're welcome.
okay. Any other questions? Please, Ladan.
Yeah. Um, Thank you, Nicholas, for your presentation. It was very interesting. Um, Honestly, I don't know anything about this, and it's a very new topic to me. So I'm curious to know about a little bit like a generic theme of your presentation. So so correct me if I'm wrong, but I'm curious to know what you're doing is having a better representation of the terrain. So in West Coast, we have a lot of like elevation and a lot of mountains. And I'll always think about this problem when, for example, you said we have a 27-kilometer grid and we are only representing the whatever that we are setting in by just single value, right? Like
Yeah.
representing in just the average elevation or whatever. Uh, is this like, are we trying to smooth the all within that grid, or are we trying to like achieve a more precise across a larger grid of like number of grids?
Yeah. No, yeah, really good question. So I let Wharf do its own interpolation. Like they have their own way of doing this, sort of, like you said, single point every 27-kilometer grids, they do like a general average. I let them do that interpolation, and then I use that interpolated value, or this interpolated result, to then reamplify the terrain. And really, yeah, we're not going to capture every detail if it's interpolated, this 27-kilometer grid spacing. If it's averaged, I'm not looking to capture every high frequency detail in that terrain. Um, but I am wanting to focus on the highest peaks of amplitude, so whether that be a mountain top or a valley bottom. Um, in theory, at these individual points, you will have some really tall peaks, some really low valleys. And the average of this is kind of going to throw that off a little bit. So that is a good question, because what becomes more important in that case? Is it the mountain peak or the mountain valley? Which what which of those is more represented in that sort of average? And by reamplifying, are we reamplifying a peak or a valley, and which of those might be more important? And that's a question I continuously ask myself. Not entirely sure how to approach it, but what I do know is, well, even if I'm using a single value at 27 kilometers, there's probably a reason why somebody is looking at a model for at 27 km grid spacing. So I'm assuming that the use of this reamplification with this already averaged interpolated domain is useful to the user who set it up that way.
Interesting. Yeah, thank you.
Sure.
I think I have, yeah, just one question. That was it. I have just another minor question about, I realized that you have like maybe two page 7, so one of them, the first one. I wasn't really sure about what is the response function. Is just like a smoothing, like where to cut off the threshold or where to smooth your train based off the response function. I couldn't actually understand what is actually a response function here.
Sure. So a response function ignoring any of these curves. So just looking at the response function here, it is essentially just that. It's just prescribing which wavelengths are attenuated and which are allowed to pass through. For my response functions, I've just simply amplified certain wavelengths. So the response functions, again, it's just a prescription. So this is something you multiply by the windowed spectrum. The response function actually exists in 2 dimensions. I'm representing it here in 1 dimension because I've actually taken the radially averaged power spectral density of the response function and I've plotted it in order to look at it in a more intuitive way, right? We're just looking at wavelength and we're looking at, well, this wavelength, for example, over here, only half of the wavelength or only half of the power of these wavelengths is allowed to be, put into the model. Whereas like a wavelength over here, the whole wavelength is allowed to be put into the model. In my cases, I'm allowing, wavelengths to be significantly amplified by a scale or by a factor. So that's essentially what a response function is. It just prescribes, when you multiply it by a spectrum, you're just prescribing which features or which wavelengths you want to keep and how much of those wavelengths you want to keep. And actually, you can look at it here. If you look at the Hanning window, so you have the route power spectrum here, and you multiply it by this Hanning window. This response functions here that are amplified look very similar to this Hanning window, except it's not like smoothly decaying over time. You have some amplification over a certain range. But you'll notice, right, like it keeps, some of these, and I do apologize here because I made these plots kind of quick. These 2D plots are actually wave numbers, whereas like this plot down here is wavelength. So here, for example, these high values are high wave numbers. So you'll see that like it's keeping all of the lower wave numbers and it's gradually sort of decreasing and then eliminating these higher wave numbers, and that's sort of the result that we see here. I hope that answers your question.
Yes, it did. Thank you. That was it. If I'm just curious, it's a very interesting topic, so I'm just let everyone else ask their question, and at the end I'll ask another set of questions. Thank you.
Well, I mean, if you have more questions, please go ahead.
Yeah, I'm just curious to know if like this response, have you come across like any method of adapting response variables? So like based on what we are looking, the landscape you're looking, for example, we have higher peaks than like in Okanagan Valley, we have lower like valley, and then with respect to that landscape, we define the response function. So it will be like amplifying, not like, in other words, just controlling the effect of the response function. So not amplifying when we have high peaks, or just reduce it when we have just mainly low like bottom values.
Yeah, yeah, it's a really good question. As of now, not really. A part of the testing here was to, amplify a variety or, two sets that start, allow higher wavelength features to go in. But then the difference of those two is that like the range of the wavelengths. So this has been sort of part of that testing that I was doing, basically being like, well, which sort of characteristic of a response function more accurately represents the terrain specifically in my domain. And that's not super general, and it might not be something that applies to every single domain. But yeah, that was part of the testing. And the way I did it was you know, throwing things at a wall and seeing what sticks, basically.
Awesome. Thank you.
Yeah.
So I think Kevin has a question. I don't know if you want to ask it or you want to read me.
Oh, I can read it here.
Yeah.
What are the key takeaways for grid operations? Yeah, really good point, right? So this is the wired group. So you guys do really focus on the grid and particularly on fires in the grid. These grids are located in very, very narrow valleys and located all over British Columbia through it goes through a lot of this complex terrain, a lot of it which is not accurately resolved in models. So my hope in this is if we're able to optimize the terrain so that we can get better verification results in terms of wind or precipitation, it can actually help forecast or help drive a better meteorological forecast for things like fire models or smoke models or anything that might be of threats to the grid.
Okay. I don't see any other questions. I'll give you the 2 or 3 seconds for people.
Oh,
Otherwise,
wait, Kevin asked another question.
Excuse me, may I ask a question?
please do.
Oh,
I have a question regarding the figure you have on top right of your poster. Actually, you mentioned a inconsistency in the verification. I want to know, it's not, I didn't completely understand whether it is a problem or it is gonna naturally happen. And if it is a problem, how do you want to handle this issue? By issue, I mean inconsistency.
yeah. So is it a problem or is it something that happens? That's a really good question. I believe it's a little bit of both. Particularly before, yes, it is something that happens because, you have stations that um, are in just, within small space, are located in different valleys and ridges that could affect sort of, how they're measuring the atmosphere around them. Um, what's a good way to mitigate this or what's a good way to look at this from a perspective of taking that into account, and it kind of goes back a little bit to what I mentioned earlier, of specifically looking at case studies that focus on the scale of the meteorological feature and if that scale could be accurately represented in the model and in the verification results. So I'm not, in a perfect world, I wish that all of them would perform better, but I think I foresee it going at a more case by case basis. So if we're trying to capture something at a particular scale, and it goes back again to sort of testing, if I know that a particular phenomenon of a particular scale affected a particular area, how well can I replicate this scale by modifying the terrain at this particular scale? And again, spatial scales. But yeah, I think it will be the case by case system. I don't think it will fix the problem for every station, or like you said, it might not really be a problem, but rather a feature of having so many stations within complex terrain. But um, that is the way that I'm thinking of approaching it is again just looking at specific case studies and specific meteorological scales that are important for whoever or whomever might be applying this to their particular case.
Gotcha, that makes sense. And after all, I want to thank you for the great presentation.
Thank you very much. I really appreciate it. Kevin did ask, can it support siting decisions? Can you elaborate on siting decisions? I don't know. I don't think, well, I guess it depends, yeah, on what siting decisions are.
Kevin is having audio problems, so maybe he can only type.
Yeah, I'm actually thinking about routing decisions because certainly avoiding hazards or areas of risk becomes a bit of a game, a bit of a challenge, and any kind of new data certainly helps. So I'm just wondering if there's possibility of plugging what you're doing into that kind of routing.
Oh yeah, definitely. Particularly when I'm looking at these larger resolutions, like for example, I'm doing a current run of a 9 kilometer domain with modified terrain. And what I'm looking at here is really just looking at the angle of incidence of a particular system as it approaches the province, and then sort of mapping out, for example, where we see the greatest amount of vertical or vertical velocity, whether that be up or down, and that can tell us like, well, in certain areas when we modify the terrain, we have this area where we might have, strong downsloping winds. Whereas like maybe the smooth model might not have showed us that. So yeah, it is basically kind of getting a picture of what certain meteorological variables look like, whether that be wind, whether that be precipitation, etc. And seeing like in a gridded response, can we identify areas? So certainly, I think it can be useful to supporting siting decisions. It's just a matter of seeing like, well, is this model, again, this is something I'm still looking into, is like, is this model work like better, or can it give us more information than what the other models may not have? And that's to be determined. And I'm, for the sake of my degree, I'm keeping my fingers crossed.
So like maybe plugged into sort of other techniques like bow tie analysis, which we see in pipeline planning and risk management as one of
Yeah,
these kind of contributors of information that.
yeah. And it is, again, yeah, I would agree with what you said. It is basically sort of like doing that sort of analysis, or maybe just identifying particular areas of hazards depending on some threshold value of a particular case.
Good. Thanks very much. And thanks for the presentation.
Yeah, no worries. Thank you.
Okay. There are no more questions. And thanks again, and a virtual applause to Nicolas. This is very great presentations, lots of questions. Thanks a lot.